Hello, hi everyone. Hope you're feeling, hope you're feeling good. And it is day 8 of studying math every day. Today it is 18 May, and it is our Independence Day where I live in basically. And it was an amazing day to be honest. And yeah, so today I was kind of busy, and there was a lot of stuff going on. So I couldn't get that much of time to study, but I'm out studying now 1 hour just to keep the study running. So I'm gonna do one session, and my internet is kind of trash even right now. I wanted to go live, but I couldn't. It was my internet is trash basically. I don't know like when I will upload this. Maybe I'm gonna upload tomorrow. I don't know. So I'll see. But right now I'm gonna study one session, and yeah, so let's stop yapping and let's start studying. I don't want to turn on the lights too. So yeah.
Imagine majoring in math.
Now let's focus on dividing rational expressions. So let's say if we have x squared minus 9 divided by 4x plus 20 over x squared plus 8x plus 15. So how can we divide these expressions? Well, first, let's turn this into a fraction. Let's put x squared minus 9 over 1. Now, perhaps you heard of the expression keep, change, flip. Well, here's how you use it. Keep the first fraction the same. So let's rewrite it. And then change division to multiplication. And then flip the second fraction. And now all we need to do is factor and cancel. X squared minus 9, we can factor as x plus 3 times x minus 3. X squared plus 8x plus 15. Two numbers that multiply to 15 but add to 8 are 3 and 5. So it's going to be x plus 3 times x plus 5. Now 4x plus 20. We can take out the GCF, which is 4, and that's going to leave behind x plus 5. Now we want to determine the excluded values. The excluded value is negative 5. You can see that here. But also, this is in the bottom of a fraction. So, which is x plus 3 and x plus 5. So negative 3 and negative 5, which correlates to this part, while it's in the bottom of a fraction, those are excluded values too. Now let's cancel. The only thing that we can cancel is x plus 5. And these two, we can write it as x plus 3 squared times the other one, x minus 3, divided by 4. So that's the final answer for this problem. Let's try this one. 4x cubed plus 32 divided by 6x squared minus 20. So that's the final answer for this problem. Let's try this one. 4x cubed plus 32 divided by 6x squared minus 24 divided by 3x squared minus 6x plus 12 over x squared minus 7x plus 10. So how can we simplify this complex fraction? If you ever see a problem like this, you can rewrite it. This is equivalent to 4x cubed plus 32 over 6x squared minus 24 divided by, whenever you see a fraction, it represents division. So we're going to divide it by the other stuff. 3x squared minus 6x plus 12. Okay, that's a terrible 2. Over x squared minus 7x plus 10. So now that we're dividing these rational expressions, let's use the keep, change, flip technique. So let's keep the first part the same. And then let's change division to multiplication. And let's flip the second fraction. Now let's factor and cancel. So 4x cubed plus 32. The first thing that we can do right now is take out a 4. And 6x squared minus 24, we can take out the GCF, which is 6. Now x squared minus 7x plus 10. Two numbers that multiply to 10 but add to negative 7 are negative 5 and negative 2. And for the other one, we could take out the greatest common factor, which is 3. And that's going to leave behind x squared minus 2x, and 12 divided by 3 is 4. So now how can we factor x cubed plus 8? Notice that we have the sum of perfect cubes. So we can use this formula. A cubed plus b cubed is a plus b times a squared minus ab plus b squared. So x cubed is a cubed, b cubed is 8, which means that a is x, b is 2. A squared, x times x, that's x squared. ab, x times 2 is 2x. And b squared, 2 squared is 4. And so that's what we have. So this is going to be 4 times x plus 2 times x squared minus 2x plus 4. And x squared minus 4, that's x plus 2 times x minus 2. Now it turns out that we cannot factor x squared minus 2x plus 4. So we just have to leave it the way it is. Now let's cancel. We can cancel those two. We can get rid of x plus 2 and also x minus 2. 4 over 6 can be reduced to 2 over 3. And we have this other 3 as well. So the final answer is 2 times x minus 5 divided by 9. That's it. So let's say if we have the polynomial 8x cubed minus 4x squared plus 12x. A polynomial is simply an expression with many terms. And we're going to divide it by a monomial, or one term. Whenever you want to divide it by a monomial, you can separate this fraction into 3 separate fractions. So basically, you want to divide every term on top by 4x. 8x cubed divided by 4x. 8 divided by 4 is 2. X cubed divided by x is going to be x squared. And 5 minus x plus 3. Let's try one more example. It's going to be x squared.
think yet, or so far, I didn't try solving any problem. I'm just kind of like doing passive learning, but I'm not like reasoning anything, and I'm not thinking even. Although this looks so simple, and all you need to do is just to always flip the sign and make it multiplication, and then also use the reciprocal of the second fraction, and then just multiply and do if there is any factoring using the different factoring methods that I have learned. Looks so simple to be honest, but I'm so feeling fatigued. I'm so tired to be honest, but I cannot even focus that much. But it is what it is. Still, yeah, you have to show up against all odds maybe. So yeah, and this looks a lot simple. Even if I try to solve one of these problems, I swear to God I can cook it. Although I'm tired, I can literally cook it. I try to take this. Like this one, oh, it is tedious to be honest. It is way too long. And yeah, you can exclude all of the values that makes x 0. Okay, so we don't need the denominator or maybe the domain to be 0, which is undefined. Yeah, so shouldn't be like that to be honest. So yeah, that is what it is at the end of the day.
And 5 minus 2
Yeah.
is 3. 63 divided by 9 is 7.
This is so simple. Maybe it is 8:40 right now, so I'm probably gonna go to sleep 10 p.m. It is 8:40 p.m. I'm gonna go to sleep 10 p.m. and yeah, I don't even know if I will be able to upload this video. I wanted to go live, but my internet was trash. So right now I want to watch like one video of Professor Leonard. I don't know how to pronounce his name. Professor Lee. I don't know how to pronounce the name. So I'm gonna watch one of his lectures. So yeah, they look kind of like, you know, easy to follow. And I'll be studying tomorrow, a lot of hours maybe. So yeah. Yeah. To the point in math, I like these lectures from this dude. Double inequality, solving compound inequalities, rectangular coordinate, creating basic scalar plots. I don't even know what that is. Graphing lines. Looking for one video of this man. Maybe algebra. This is so simple to be honest. Division of whole numbers. Maybe I'm about to watch a lecture that I wanted to watch 1 point. Introduction to fractions. Dude. Lectures are way too long. His lectures are way too long. That I cannot do it maybe. I don't know. Maybe I'm about to go. My playlists. I think this today is just like me scrolling on YouTube instead of me studying math. So yeah, it happens. So maybe I have to watch this video to watch it. Basically, I already watched the video. I already watched the video, but I'm about to watch it because like when I was studying imaginary numbers were not making sense to me. I think so far I understood in a way, but like still I'm missing something to be honest. okay. So I watched this lecture, and yeah, it makes sense. He was even explaining where these numbers like started, how we started with real numbers first, not real numbers basically, but like positive numbers from 1 to like to infinity, because like they represent something that we can see physically, because like we got one pen and that's why one exists, right? And we're gonna get two to represent it, two objects basically. That's how this number is getting to the place first. And then we invented -1, which is like used for maybe banks, like maybe if you are owing some money to somebody, that means it's like minus to him. So it's something like that. So he also explained why we ended up this. So he was doing some type of a graph that was like x and y, where x, or maybe the horizontal axis, was just like the real numbers, and also the vertical axis was the imaginary numbers. That's how the lecture was, and that's the like the amount of information that I can retain from this lesson. But it is basically like why imaginary numbers are there first. It's like they don't even make sense to me yet, like so far. So yeah, one time maybe they will.
I'm a postdoctoral fellow at the NASA Jet Propulsion Lab, and in this video I'm going to show you how imaginary numbers are not imaginary. In fact, the name imaginary is really stupid, and we should probably stop using it. And I'm going to show you the math perspective on imaginary numbers, and I'm going to show you the physics engineering perspective, which is kind of the math perspective, but with the application in mind. So what I have over here is the way I is usually thought of, which is I equals the square root of -1. And then I have something else over here that says I equals 90 degrees. Now, what does that mean? So for the rest of this video, I'm going to first go over this, what it means, how we came to this, and then I'm going to show you what this means, I equals 90 degrees, and I'm going to erase this, and I'm going to draw a little graph that's going to make things a lot more intuitive, so you can finally visually understand what imaginary numbers are, and going forward you can hopefully think of them a little bit different. So where did this come from, this I equals square root of -1? Why do we have it, and why are people thinking about it all the time? Well, this is basically, if you've taken any type of high school math or college math or anything of that nature, you've probably learned that when you're trying to solve for an equation, like let's say, I don't know, y equals, I don't know, like x squared minus 4. Well, the way you try to solve for the roots, or you try to find a solution for this, for it to be true, you set it equal to 0. So you have 0 is equals to x squared minus 4. So then you have x squared equals 4. You have x equals plus or minus 2, right? Because you take square root of each. And then you just go ahead and plot this. And then what that basically looks like is you have -1, 2, 3, 4 over here. You have 4. You have a -2. You have a 2. And then you basically have a parabola that looks like this, where these are the two solutions or roots, right? And that basically your algebra teacher in high school tells you, well, that's basically how you do it. And then something terrifying happens, right? You are faced with an equation that does not look like this. You're handed an equation at some point that says, instead of x squared plus 4, you'll get one that says like, I don't know, plus 1. And you start freaking out because you try to do the same thing and you're like, okay, x squared is equals to -1. Well, take the square root of both sides, square root of x squared, square root of -1. This becomes an x, and this becomes the square root of -1. And like, what is that? What does that even mean? What does the square root of -1 mean? And then you're basically just told, oh, that is I. And then you just get like an equal sign, and it's like I. And then going forward, you know that I is the square root of -1. And like everyone kind of claps and moves on, and no one understands what the hell I is.
My chair literally broke, I guess. I don't know.
This is for the people who are like only doing like pen and paper math and kind
literally
of have
broke.
no
I
sense
swear
of what's
to God.
happening in the real physical world.
It did.
Now, I'm going to show you the physics
don't know where
engineering
though.
perspective, something way cooler and way more intuitive. But before I explain to you what an imaginary number is in terms of physics and engineering, I'm going to first ask you, well, what even is a number, right? Before we talk about imaginary numbers, let's talk about numbers, right? Numbers are things that we basically use to count things. Like I have one eraser in my hand right here. There's one board. There's multiple chalks. There's a bunch of, well, there's like a couch, 2 couches. So you basically use the number to count physical quantities. At least that's how we use it in engineering and physics in the real world.
It literally made some
basically
some-
numbers can be
some-
represented on a
some
number line,
noise,
right? Which
basically.
basically say we have a number line over here, and it starts at like 1, 2, 3, and it goes all the way to infinity, right? And you've probably heard of like the different kinds of numbers, like the rational numbers and whatnot, the natural numbers and whatnot. And then some people thought, okay, well, what happens when you have no numbers? What happens when you have zero quantity of no quantity of things? Well, that's what 0 is, right? So we basically added 0 to that number. Now, beyond that, we thought, okay, well, what about if you start going the opposite way? What if you're going in the opposite direction and you start having things like -1, -2, -3? And this is where things get tricky, because immediately, philosophically and intuitively, you're like, well, what the hell is a negative number? What does that mean when a number is negative? We know what it means when a number is positive. That's basically how many things there are that you can count. We know what 0 means. 0 means there's the absence of it. And, well, what does a negative number mean? Well, the negative number does not imply that the quantity itself is negative. The quantity remains the same, but it just implies that now we are going in a different direction. And this can be really useful in an example such as like banking or money, for example, where let's say if I give you $20, you earn $20. And then if I take away $20 from you, you lose $20. And we realize that negative numbers are something that's very useful, that teach us like values that are bidirectional, that can go one way or the other. And for example, if you're a student and you have student loans, you can say that you're walking around and you have negative money, right? Like you have negative money tied to your name, and that's basically money that you owe. And that's basically one way we understand negative numbers. Now here's where things get really, really cool, is instead of thinking the negative number, like when you multiply something by -1, let's say, I don't know, I have a value which is 5, and let's say I multiply it by -1, what exactly am I going to do to it? I'm basically going to take that sign, I'm going to add it, so it becomes -5, right? And you've probably learned this in school, where like you apply anything by a negative number and you get the negative of whatever that is. Now here's what's actually happening, is whenever you're multiplying on this same line, all you're doing is you're doing 180-degree rotation. You're basically going in this direction, you're like, oh, nope, we're going to start going in this direction. So if I have this 3 over here, and I'll multiply it by -1, well, what's going to happen? Now I'm going to have -3, which means I'm taking this arrow over here, this value that is 3, rotating it 180 degrees, right? And then I'm going to end up with this -3 over here. So in a way, you can think of a negative number multiplication as 180-degree rotation, okay? And it makes sense, because if I'm going this way, and now I'm going like negative, the complete opposite of it, now I'm going complete opposite way, right? Makes sense. Now here's where things get really cool. Well, you might ask, well, okay, Ali, this is happening on a single dimensional number line. What happens if we have 2 dimensions, right? And I'll get a little bit why numbers have to be 2-dimensional sometimes, or why most numbers are 1-dimensional, but sometimes we need 2 dimensions to describe things. I'm going to explain that in a little bit, but let's just stick with this example. So suppose, again, I have my 0, 1, 2, 3, -1, -2, -3. Well, what happens if instead of doing 180 degrees, what if I only want to rotate 90 degrees? Well, guess what? I can multiply by I, because whenever you take a number such as 3 and you multiply it by I, and you get like 3i, all you're getting is this axis over here, which is like 1i, 2i, 3i, and so on. This is like -1i, -2i, -3i. So basically, if I'm over here, and again, I'm going to use a different color to explain it. If I, again, have my number 3 at the arrow line, and instead of rotating 180 degrees, I only want to rotate 90 degrees, I'm not going to multiply it by -1, I'm going to multiply it by I. And then I do this rotation 90 degrees, and then I end up with 3i. But now here's where it gets cooler. What if I want to do another 90-degree rotation, and I multiply by another I, because we said that I is basically a 90-degree angle. Then I take this 3i times another I times I is basically -1, because I is the square root of -1, and basically I'm rotating all the way over here. So I could either take this 3 and multiply it by 1, and that's basically 180-degree rotation, or I can take the 3, multiply it by I twice, and then I'll get the exact same thing, which is 180-degree rotation. So you can think of I as just something that allows us to visualize math as two-dimensional numbers, numbers as two-dimensional rather than unidimensional. And by basically multiplying something with I, we're able to rotate rather than just like go back and forth between positive and negative numbers. Now I know what you're thinking. Well, like why the hell would a number be two-dimensional? What does that even mean? In which cases do we need numbers to be two-dimensional? And why is there another axis over here, right? And here's the reality is that even though this is called real and this is called imaginary, when you're taking this value and you're rotating it by 90 degrees, it's not any less real than it was when it was over here. It has just rotated, right? So one example you can think about this is if you're looking at a signal at certain, as a signal goes by, so like let's say for example, sine wave. And actually I'm gonna give you a very simple example. Let's compare this eraser and this chalk over here. And let's say I'm trying to plot how they vary in size over time. So let's say that I have this eraser, and as time goes by, let's say, I don't know, like the length of the eraser, we're gonna call this L. And if we were to measure this, I don't know, like this probably be like 10 centimeters or so, it would just hang around at 10 centimeter mark, right? Or like we say, if it stays like at 10 centimeters, or if it's even, or if it's odd one out. Now let's take a look at this chalk. If I measure how this chalk varies over time, and let's say again, this is length, and let's say this is time. Obviously, the more I use it, let's say I'm using it like constantly, like in a linear rate. It's going to start out with a certain length, and it's going to keep going, and it's going to keep going down linearly in a single line like that, right? But now here's what's cool. Let's suppose I do a different kind of function where I say, instead of plotting how much the chalk is getting shorter, let's say I want to oscillate from, I want to say that the chalk, like I want to oscillate between when it goes from even to odd. So let's say it starts out at 10 centimeters, and then it goes to 9, and then it goes to 8, and then it goes to 7, and then it goes to 6. And I want to model that. I want to model that every time it's an even number, like I get one value, and every time it's an odd number, I get another value. What I'm gonna get as a plot over here is something that looks like this. Like it starts out even, and then it goes odd, and then it's even, and then it's odd, and then it's even, and then it's odd. And depending on where I am looking, depending on whenever I take a snapshot in time, because this goes on at 8, and then it goes 7, and then it goes to 6, and I want to model that. I want to model that every time it's an even number, like I get one value, and every time it's an odd number, I get another value. What I'm gonna get as a plot over here is something that looks like this. Like it starts out even, and then it goes odd, and then it's even, and then it's odd, and then it's even, and then it's odd. And depending on where I am looking, depending on whenever I take a snapshot in time, because this goes on in time, all I'm basically doing is the value is basically rotating in a circle. And let's say here is even, and then here is odd, okay? And then it goes from like 10 to 9 to like 8, 7. Now, a very simple way to think about this, well, what about what happens in between? What about like 8.5? And then what about like 7.5? And so on. So you can think of the reason we include imaginary numbers is we're interested in beyond just like what happens at the two extremes. We're interested beyond of what just happens, let's say, between summer and winter. We're curious about what happens in fall and what happens in spring. And what happens in between? What about all these values over here that exist somewhere between the real and the imaginary number line? Well, guess what? Those are called complex values. And that's in between. What about all these values over here that exist somewhere between the real and the imaginary number line? Well, guess what? Those are called complex values. And that's actually another stupid name because they are not really complex. Complex does not mean they're complicated. Complex just means that if you were to plot them and draw them into an axis over here in X and then in Y, they are made of one component here, which again we're going to call real, and then there's another component here which is called imaginary, and then these guys are basically modeled. One way you can think of them is using this equation, e to the j theta. It's I use j because I'm an electrical engineer, and then that can be modeled as a cosine theta plus j sine theta, which basically is telling you that whenever you have a signal at any point on this domain, and you can model it by its magnitude and phase or degree, or you could basically break that. Oh, this kind of looks like a big mess.
Dude, the stuff is getting complicated, to be honest. This part
So
is
basically,
just...
whenever I have like a signal or like some value that I'm representing, I can either represent it.
I don't even know cosine sine. Like, I know in a way, but like, no, I didn't study it. I didn't study it yet. But like, I took it back in high school, but I don't remember none of it, to be honest. None of it. And I didn't even understood like at the first place back in high school. I was just like ignorant, you know. But yeah, it is what it is. I'm kind of close, I guess, but yeah, it is fine. So yeah, I think I got how many minutes left? I got 7 minutes left. So yeah, I'm just gonna call it today. I know this is not good, but like it is what it is. You have to just like battle the situation as you face it, I guess. It's just like this won't be the same, but just don't give up and show up against all odds, no matter what. Just show up. That's what makes sense. And yeah, that this is why I'm doing this entire thing. Basically, this is why I'm doing the entire series. I don't want to miss a day. I don't know how long it will like take me to break the chain, but like all I want to do right now is just to don't break the chain no matter what. Just like at least to show up and study something. Like right now, I think I get the time, but like I don't have the energy to do it. Okay, and I'm so sleepy. But all matters is just like showing up. Maybe I'm passive, like learning, just like learning something without any reasoning and doing any problems. But like this is how it should be sometimes. This is the first time that I'm doing this. Like on the Friday, I did 1 hour, but like basically that day it is a weekend for me, and I don't even want to do something. Okay, I was just reviewing stuff. Although I was thinking and doing a lot of like mine job. I don't know, just like reasoning a lot of stuff. But still, I did it. So it was an amazing day, to be honest. It was an amazing day for me. It was an amazing day for me. It was an amazing day for my people. And it was an amazing day like for my country. It was just like a big day and a huge day for us, and we won't forget it. So yeah, I'm so glad to be here and to yap and watch something and think like I studied something. Well, I didn't, but yeah, it is fine, I guess. Yeah, this is how it should be. So yeah, so just want to hit the sack, go sleep early, and then wake up early to do maybe 3 sessions tomorrow early in the morning at 6 a.m. That's what I want to do. So yeah, right there, my flag. So yeah, so see ya.